Today, on how it's made. Suits of armor. Working the night shift. Street light poles. We shed some light on how they're produced. Bent hardwood. We'll visit a factory that doesn't give you the straight goods. Membrane switches. The secret behind those appliance touchpads. If you're the type of guy who finds wearing a tie uncomfortable, try sporting a suit of armor. Armor reached its peak during the battle-filled 15th century. Initially, it was made of chainmail, tiny rings of metal linked together. Then, for greater protection, knights began wearing plate armor, suits made from large pieces of steel. Today, armorers make this obsolete battle gear mostly for historical reenactment buffs. This workshop specializes in custom-made suits of armor. The armorer has to take 45 different measurements just to prepare the pattern. He traces each pattern piece on a steel sheet that's about 1.5 millimeters thick. Then he cuts along the trace line with a bandsaw. This is the breastplate, which covers the chest and abdomen. Now he begins to shape the piece using an automatic hammer. There's no mold or template to guide him. He works strictly by eye. Now that he has the basic shape, he refines it using a manual hammer. He strikes the metal against an upright log, a bag of lead beads cushioning the blows. This prevents the metal from deforming. A few lighter blows without cushioning in select spots to finalize the shape. Until now, he's been hammering the inside of the breastplate. Now he works the outside. He smooths the metal surface, a process known as planishing. Now, using a different automatic hammerhead, he stretches out the breastplate's bottom edge to form a rim angling outward. He places the piece on an anvil, then using a manual hammer, planishes the rim. When you wear this heavy metal breastplate, the rim takes some of the weight off your shoulders by distributing it over your hips. The armorer checks the shape, then makes any necessary adjustments. Now, using several different hammers again, he works his way around the rest of the breastplate, gradually rolling the edge onto itself to form a rounded lip. Rolling the metal onto itself to form the lip reinforces the perimeter of the breastplate, and the rounded edge prevents the sharp metal from cutting the skin. The breastplate is now ready for the finishing touches. First, the armorer smooths the surface with medium grit sandpaper, then with fine grit sandpaper, then the last step with fine grit paper and a polishing compound. Some breastplates have an articulated styling. For this model, the armorer uses 3 brass rivets to attach the sections. He fastens them loosely to enable the pieces to move. Then, using rivets again, he attaches leather straps. A suit of armor is made up of about 20 different components, such as the front and back shin guards, called greaves, armor and leather gloves, called gauntlets, shoulder pieces, called pauldrons, and of course, the helmet and visor. A knight would don his suit of armor from the bottom up. Otherwise, the weight of the top components would have him keeling over half-dressed. In the Middle Ages, a suit of armor cost as much as a small farm. It was a prized luxury only the nobility could afford. Being a modern-day knight in shining armor doesn't come cheap either. A base model suit costs about $3,000. An elaborate one, up to $20,000. We take well-lit streets for granted, but there was a time when venturing out at night meant traveling in complete darkness. In 1814, the first gas lights lit up the streets of London, England. The first electric streetlights illuminated a public square in Cleveland in the United States in 1879. These streetlight poles are made of what's called composite, a combination of fiberglass and epoxy resin. Epoxy resin is a gooey liquid plastic mixed with a hardener. The factory constructs each pole on a mandrel, a long tapered metal cylinder. Workers first lubricate the surface. Then they take what's called fiberglass filament, a string composed of 2,200 tiny fiberglass strands. They'll wind dozens of filaments around the mandrel to create the pole. But first, the filaments go through a bath of epoxy resin. This resin is moldable, and once it's heat-cured, maintains its shape. Once the filaments come out of the bath, a machine called a filament winder wraps them around the rotating mandrel. The speed of rotation in relation to the speed of the winder is critical because it dictates the angle of the fibers. The lower the angle, the more that part of the pole will be able to withstand the wind and provide constant, stable lighting. When a pole bends in the wind, the light appears to flicker. The number of filament layers depends on the design of each specific pole, and that's determined by a couple of factors. First, the type of light fixture the pole will hold. The bigger the fixture, the stiffer the pole has to be. The other factor is wind. The windier the location, the stronger the pole has to be. Once the winding's done, the mandrel moves on to the curing station. They pump pressurized steam into the hollow inside of the mandrel. The heat kickstarts the hardener in the epoxy resin. This solidifies the resin and cures it. The mandrel rotates so that the pole cures evenly. Curing time depends on the length of the pole and how many filaments it's made of. To help extract the pole, they pump cold water through the mandrel. This makes the steel mandrel contract, loosening the pole. Remember how workers lubricated the surface of the mandrel before winding the filaments? Because of that, the pole just slides off. The pole now moves on to the finishing stages. First, an automated sander works the surface. The customer can order from a choice of surface textures, from smooth to rough. Sanding takes just a few minutes. Now a saw makes a neat cut at the top of the pole where the metal tenon will go. A tenon is the component that'll hold the light fixture to the pole. This particular model has an arched mounting arm. The composite has cooled a bit since curing, so they reheat it to make it flexible. After a bending machine makes the curve, they spray cold water inside to cool the material. This registers the curve in the resin's memory, setting the bent shape. Now they cut out the hand hole, the opening through which the electrician will connect the underground wire to the fixture wiring. Workers then spray the pole with urethane paint. The paint acts like sunscreen, protecting the composite from damaging ultraviolet rays. This grommet hole will connect to the underground pipe that contains the electrical wires. After installing a cover over the handhole, it's time to assemble the parts. The underground pipe to the pole, and the pole to the tenon and light fixture. Many products have rounded components made of solid hardwood. Often the companies that make these products hire factories that specialize in wood bending to prepare these components for them. Bending wood may sound simple, but it isn't. It takes a lot of preparation and skill to bend wood without cracking it. The best type of wood to bend is hardwood. Its fibers react better to heat and moisture than softwood fibers do and therefore curve nicely. If you bend softwood, it wrinkles. The wood first goes into an outdoor dryer to bring its humidity level down to between 15 and 20%. This prevents the wood from expanding and contracting after it's bent. This air drying process takes up to a week. Once the wood is dry, a powerful trimmer saws the pieces to the required length, an edger to the required width. Now that the wood pieces are the right dimensions, they go into what's called a steaming box. This superficially rehumidifies them so that they become somewhat flexible. This takes from 10 to 45 minutes depending on the type of wood and its thickness. This humidity will later evaporate out of the wood. Now the pieces go into a press sandwiched between two forms in the shape of the curve to be made. The press applies both pressure and heat. Pressure to bend the wood. Heat generated by a high-voltage electric current to cure it, setting the new shape. How long the pieces stay in the press depends again on the species and dimensions. Generally, it takes from 20 minutes to an hour. Making this particular type of curve is called crown bending. Workers measure each piece against the template to ensure the curve is just right. The factory uses the same process to bend these pieces into a different shape. It's critical to use just the right amount of heat and pressure. Too high a temperature would burn the wood. Too much force would crack it. These straight pieces of wood will become the rounded backs of Windsor-style chairs, which is why this type of bending is called Windsor bending. Workers humidify the wood in the steaming box, but will shape the pieces using a pressure-only process. They mount what's called a bending mold onto a hydraulic press. This machine uses just pressure to bend the wood around the mold. No heat this time to immediately set the shape. Instead, once the press curves the pieces, workers hook up a chain to temporarily hold the shape. Then they transfer the bent pieces to a heated indoor dryer. The drying process takes between 2 days and 2 weeks, depending as before on the type of wood and the dimensions. Once the wood dries out, the curve is permanent. There are many wooden products that require bent components. This wheel for a horse-drawn carriage, for example. Back to the Windsor chairs now. A dowel machine rounds off the bent pieces. Before shipping the pieces out, workers run them through a sander. This prepares them for the furniture factories who'll varnish or stain and varnish them. Upon receiving these chair backs, the furniture factories will assemble them to the straight parts of the Windsor chairs. The term membrane switches probably means nothing to you, but chances are you use them or at least see them in use daily. Membrane switches are those soft touchpad buttons on the controls of many electrical and electronic devices. For example, the buttons on a microwave oven or on a cash register. The surface on the appliance's control panel is called the graphic overlay. It's a sheet of plastic on which they print the design of the control buttons. Each button has a membrane switch underneath it. To make this graphic overlay, they first laser print a sheet of acetate film with the design, as many copies as will fit. They lay the film on a polyester screen coated with a light-sensitive chemical. Then, using this machine, they expose the screen to 2,000 watts of ultraviolet light for up to 6 minutes. The light hardens the chemical on the parts of the screen that aren't shielded by the design on acetate. This blocks the screen's minute holes everywhere except in the design. Workers remove the acetate film and rinse off the shielded chemical that didn't harden. Now they have a screen stencil of the design they're going to print. Workers dry off the screen and install it on a printing press. A squeegee drags the ink across the screen, pushing it down through the open holes, printing the design onto the overlay plastic. Ultraviolet lamps cure the ink in a matter of seconds. Each color of the design goes on separately. That means that there isn't one printing screen for the entire graphic overlay, but rather a separate screen for each color. Meanwhile, on another screen printing press, they print the circuitry layout onto transparent plastic. The ink contains silver, which conducts electricity. The circuitry layout will go behind the graphic overlay. Again, they print several at a time. Once the printing's done, it's time to assemble the layers that make up the membrane switch. First, the circuit layer goes onto an adhesive sheet. A roller ensures a solid, airtight bond. This spacer sheet will separate the overlay and circuit layer to prevent contact between the two from being continuous. Over each circuit goes a dome made of nickel-plated stainless steel. This forms an electrical contact over the circuit that must be forcibly pressed in order to activate the circuit. They adhere a polyester sheet to hold the domes in place for now. After cutting out each circuitry layout and each graphic overlay, they expose the adhesive backing on the overlay and stick it to the circuit layer. The membrane switches are now complete. This control panel is for a hospital bed. Some membrane switches have a light-emitting diode, or LED, a tiny colored light that goes on when you press the switch to confirm contact. The factory's robotic machines deposit 2 drops of epoxy paste on the circuit layer wherever an LED will go. The paste contains silver, again to conduct the current. A robot then picks up the LEDs and deposits them on the drops of paste. The robot then puts a dome on each circuit, creating an electrical contact. The red light you see is a camera checking the positioning. Testing equipment runs a current through the circuitry to make sure that everything works. Then a drop of transparent sealant goes over each LED. The sealant hardens under ultraviolet light, holding everything solidly in place. Now workers remove the panel from the automated line and plug it in. Lighting up all the LEDs helps them position the graphic overlay properly. This control panel is for a wall oven. No LEDs on this model. And instead of a dome behind each button, they print an electrical contact using the same conductive silver ink they use to print all the circuitry. After rolling on the graphic overlay, they peel off the protective plastic, then flip the control panel upside down and snap it into its cover. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.